Hello, everyone, and welcome to this short talk about the weight-dependent random connection model. In this specific talk, limited or restricted rather to one dimension. We will see that actually has some nice sort of consequences for our results. This is joint work with Lukas Lüchtrat and Christian Münch, and without any further ado, let's just get started. First of all, how do we build our random connection model? So what types of graphs are we considering? Well, first of all, our vertices are just points of a Poisson point process of intensity 1 on the real axis, but all of these points are also equipped with uniform marks between 0 and 1. Next, how do we connect these marked vertices? Well, edges are drawn uniformly at random between all pairs according to what the distance between the two vertices is and what their marks are. More precisely, a marked vertex xt connects to a marked vertex ys with a probability of the following type. So let's perhaps have a closer look at this probability. So we have a couple of functions here, starting with the profile function rho on the outside. This is the function that we want to be integrable and non-increasing, and it's the function that controls how our graph is spatially embedded into or onto the real axis. So you can see that, for example, if the distance between x and y increases, because this function is non-increasing, then the connection probability can only decrease, which is exactly what we would expect. Next, we have the function g, the kernel function, which we require to be symmetric and non-decreasing in both arguments. And this is the function that basically controls what influence the marks of the vertices have on the connection probability. I should mention here, we want this function to be non-decreasing because we treat marks close to 0 as being powerful marks and marks close to 1 as weak marks. This sort of comes from how these models were built historically. Finally, we have the beta parameter, which is the temperature parameter, and it does exactly what one would expect it to do. The higher beta is, so the higher the temperature, the more activity we want to see in the model, so more edges get formed. And again, because the profile function is non-increasing, that is precisely what happens. Now let's have a closer look at a couple of kernel functions that we might be interested in. So there's a long list of possible kernels, such as the plane kernel, which just completely omits the marks of the vertices, the product kernel, where the power of the vertices simply multiplies. And here we have this additional parameter gamma that controls just how strong the effect of the marks is in every given kernel. We have the max and min kernel that I will not go into right now. We have the sum kernel, which is tightly related to the Boolean model, as we will see in a slide or so. And then there's the preferential attachment kernel, where, as the name implies, we end up with graphs that are of the preferential attachment type, meaning very powerful old vertices connect much better than very young vertices. So that's as far as I want to tell you about the kernel function. So now let's look at profile functions. So far, I've only said they should be integrable and non-increasing. We can take a couple of additional assumptions. First of all, that this function maps onto the interval 0, 1 is fairly self-explanatory, since we actually want to be dealing with probabilities. And without loss of generality, we can also assume that not only is the function integrable, but actually it integrates to 1. Now, let's take all of this together and have a look at a concrete example to see how all of these functions and parameters interact with each other. So we have up in the left corner still this fully general connection probability. And in the right corner, let's now, for example, consider the sum kernel, which I already mentioned is tightly related to the Boolean model. So what's the probability of two marked vertices connecting if we have some general profile function, but this concrete sum kernel in the connection probability? Well, then we can interpret the connection probability exactly as one would interpret it in the Boolean model, since we then compare the rescaled mark t to the minus gamma that corresponds to the vertex x and the mark rescaled to s to the power of minus gamma for y. And if we interpret this as radii of balls, then the question is, what are these radii, or how large they are compared to the distance between x and y? And this is precisely what we end up plugging into the rho function there, because we just plug in the kernel function times the distance. And then if this ratio is smaller than 1, it means that the radii together are larger than the distance. So if our rho function was just an indicator function, for example, then we would connect. And if the ratio is greater than 1, meaning the distance is greater than the sum of the radii, we would not connect. Again, that would be precisely what an indicator function there would do. For our questions, we will actually not consider indicator functions for the profile function, but instead we will work with profile functions that have polynomial decay at rate delta. Now, how does this sort of affect the connection probabilities? The logic is still the same. So we still compare for this specific kernel the sum of the radii and the distance between the 2 points. But now, instead of this being a binary choice between connect or not connect, this gives us a probability with which an edge is formed. And this probability is decreasing as the distance between the 2 vertices increases if their weights remain the same. And likewise, this probability is increasing if the distance stays fixed, but the weights increase, meaning the marks go to 0. Now, with that out of the way, we sort of understand how the model works. The question that I want to answer is, if we have a profile function rho and a corresponding delta, and a kernel function g with the corresponding gamma, does the graph contain an infinite connected component, or can it contain an infinite connected component? And I will not waste any time, especially since my watch seems to want to talk to me, and get straight to the statement of the result. So if we have a polynomially decaying profile function with polynomial decay greater than 2, and we have a chosen kernel function, then we can sort of see 3 possible situations. We can be in the situation, in the regime, where an infinite component always exists, regardless of what the activity of the model is. Meaning, even if there's almost 0 activity in the model, we still end up with an infinite component. That's the first situation. On the other end of the spectrum, we have the situation when, regardless of what the activity is, we never have an infinite component. And then there's the middle case where an infinite component can exist, but there needs to be sufficiently high activity for that to happen. Graphically speaking, this is the situation. So we have the 3 regimes. On the left, never an infinite component. On the right, always an infinite component. And in the middle, an infinite component only if the temperature parameter is high enough. Note that this phase diagram holds for the preferential attachment sum and mean kernel on the right-hand side and in the middle side. However, the left regime, the no infinite connected component regime, we were only able to prove for the sum and min kernel. For the preferential attachment kernel, that's still ongoing. Now, back to our main result. Before I conclude, I'll just quickly outline where each of the results sort of comes from, what's the key idea behind it. Starting with the always having an infinite component. That one is easy since it's a direct consequence of another result, namely the robustness of the model, which will actually be discussed in a separate talk in this session by my colleague Lucas. The interesting case, at least for this talk, is the middle case, where we can have an infinite component, but only if we have sufficiently high activity in the model. And how we get to that is as follows. We start at some very large scale. And we can show that starting at that very large scale, meaning considering a very large interval, that interval can connect, so form edges with neighboring intervals of the same size with a very high probability. And then once we've connected sufficiently many of such intervals, we treat that as the new interval and repeat the process, connecting it to neighboring intervals that are now also bigger, and so on and so on. So we build scale by scale, bigger and bigger intervals. The only problem is that although all of this happens with probability going to 1, and therefore almost surely, it needs to start at some stage. And that's where the temperature parameter comes in, because if we have high enough activity, we can basically guarantee that at some very large scale, this process starts, and then almost surely the infinite component gets built. The third case, where there is almost surely no infinite component, basically comes down to proving, and using correct scaling, that the probability of no edge jumping across an arbitrary point on the real axis is strictly greater than 0. And then by translation invariance, we get by standard interpolation type arguments that an infinite component simply cannot exist, because it will almost surely at some stage get sort of cut off from the left and cut off from the right. And that's it. Thank you very much for your attention. And I hope to see you all in the question session later on.